Hello, and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be exploring systems of three linear inequalities. Now, before we do that, let's review what a system of linear inequalities is. A system of linear inequalities in two variables consists of at least two linear inequalities that are graphed on the same coordinate plane. The solution of a system of inequalities is the set of all ordered pairs that make the system true. So in this particular picture, the solution set is this commonly shaded area, and every ordered pair within that commonly shaded area is said to be a solution. All right. In example 1, it says use substitution to determine whether the ordered pair is a solution to the system. So if we don't have a graph given to us, then the only way we can determine if an ordered pair is a solution is to substitute that ordered pair into each inequality and determine if it satisfies or makes that inequality true. So let's look at our first ordered pair, 1, 3, and we're trying to determine would that 1, 3 fall in the solution area if I were to graph the system. So to do that, let me write down our top inequality, opposite x plus 2y greater than negative 8. Now I'm going to replace the variables with parentheses. I'm going to have to write pretty small to do this. And I want to plug in a 1 for x and the 3 for the y. So that would give me negative 1 plus 6 is greater than negative 8. And negative 1 plus 6 is 5. And 5 is greater than negative 8. So the ordered pair made the first inequality true. Now, that doesn't mean it's a solution yet. It has to make each inequality true. So now I'll try my next one. Opposite x minus 2y greater than or equal to negative 4. Replace the variables with parentheses. And I will plug in my ordered pair, 1, 3. And negative 1, this would be negative 6 greater than or equal to negative 4. So I get negative 7 is greater than or equal to negative 4. Well, that is false because negative 7 is smaller than negative 4. So I don't even have to do the third inequality because if I get even one false, then that means that ordered pair is not a solution because it has to make all three inequalities true. All right, let's look at B. Here our ordered pair is 2, negative 1. So let's take our top inequality and replace the variables with parentheses and plug in our new ordered pair, which is 2, negative 1. So this would give me negative 2 minus 2 greater than negative 8. So negative 4 is greater than negative 8. That's true. All right, take your second inequality and replace the variables with parentheses and plug in our new ordered pair, which was 2, negative 1. So negative 2 plus 2 greater than or equal to negative 4. So 0 is greater than or equal to negative 4, and that is also true. Now to check your third inequality, x is greater than or equal to negative 2. Our x value of our ordered pair was 2. So is 2 greater than or equal to negative 2? It's true. So it worked in all three. So this ordered pair was a solution. In other words, if we graph it, it would fall into the commonly shaded region. All right. Example 2. Graph the system of inequalities and find the vertices of the triangle formed by the constraints. So each one of these inequalities is known as a constraint. It's like a boundary line. So to graph these, we're going to have to put them in slope-intercept form. In other words, we're going to have to get the y by itself. So on our first inequality, we have 2x minus y is less than negative 1. Let's start by moving the 2x to the other side. So when we do that, we get negative y is less than, if I move 2x to the other side, it'll be negative 2x minus 1. Now I need to divide each term by negative 1. So negative y divided by negative 1 would be positive y. My inequality would reverse to greater than. Negative 2x divided by negative 1 would be positive 2x. And negative 1 divided by negative 1 would be positive 1. All right, so now I can graph this inequality. So my y-intercept is positive 1. I have a slope of 2, so up 2 over 1, up 2 over 1, down 2, left 1. And I'll just keep going here. Just going to fill up my entire grid. That'll help me keep my line straight. Now, we're going to graph this with a dashed line. And then we lightly want to indicate where it would be shaded. So this inequality is greater than, so it's going to be shaded above the line. So I'm just going to draw an arrow saying we need to shade that way. All right. Now let's do our second inequality. We have negative 2y is greater than, I want to take that positive x and move it to the other side, which would make it negative x minus 8. Now we need to divide everything by negative 2. So negative 2y divided by negative 2 would be positive y. Greater than would become less than. Negative 1x divided by negative 2 would become positive 1/2 x. And negative 8 divided by negative 2 would become positive 4. So let me graph this one in a different color. So I'm going to start on the y-axis at positive 4, 2, 3, 4, and go up 1, right 2, up 1, right 2, and go the opposite way, down 1, left 2, down 1, left 2, down 1, left 2. Just fill up your entire grid. All right, and this will also be graphed with a dashed line. Now, this symbol is less than, so for this graph, I'm going to shade below. Okay. All right, my third inequality, let me grab a different color here, is going to be y is greater than or equal to negative 1. So this is there's only one variable here, so this is a horizontal line passing through (0, -1). So here's 0, -1, and I want to draw a solid horizontal line. Okay. Now this symbol is greater than, so I will be shading above this line. Now notice the only part of the graph that it was shaded 3 times was this region right in here. So we formed a triangular region, and the question asked us to find the vertices. So let me darken those in here. There's one, and there's one. So let's list those vertices. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, -11, -1, -1, -1, and 1, 2, 1, 2, 3, 4, 5, and 2, 5. All right, example 3. Graph the system of inequalities and identify the vertices of the solution set. So we're going to do the same process again. I'm going to take each inequality, I'm going to get the y by itself, and then plot each inequality. So for negative x plus 2y is greater than -8, I would want to take that negative x and move it to the other side and make it positive x. So 2y is greater than positive x minus 8. Now divide everything by 2. So 1x divided by 2 would be 1/2 x. -8 divided by 2 would be -4. So to plot this, start at -4 on the y-axis, up 1, right 2, up 1, right 2, up 1, right 2, up 1, right 2. Okay, and this will be a dashed line, and we're going to indicate which way to shade. So this was greater than, so we're shading above. Okay, all right, next inequality. We're going to move that negative x to the other side and make it positive x minus 4, and then divide everything by negative 2. So y would become less than 1x divided by negative 2 would be negative 1/2 x, and negative 4 divided by negative 2 would be positive 2. Let me grab a different color here. So starting at positive 2 on the y-axis, I'm going to go down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2. Oh, and this one, I'm sorry, it had a solid line under it. So we need to graph this inequality with a solid line. Try to get that straight. Okay. Now let's draw an arrow to indicate where this is going to be shaded. Because it's less than, it's going to be shaded below. All right. Now our last inequality is x is greater than or equal to negative 2. So this is a vertical line because it starts with x. And it's going to pass through negative 2, 0. So a vertical line, it's going to be solid. Let me grab a different color here. It's going to look like this. And it is greater than, so it's going to shade to the right. So now I hope you can see that the commonly shaded area, let me highlight it, will be this triangular region formed right in here. And they want the vertices of the triangular region. So let me darken those in a little bit for you so that we can find out what they are. So negative 2, 1, 2, 3. So negative 2, 3 is the top one. Negative 2, 1, 2, 3, 4, 5. Negative 2, negative 5 is the bottom one. And then 1, 2, let's see, 1, 2, 3, 4, 5, 6, 7. Or is it 6? 1, 2, 3, 4, 5. 6, negative 1 is our final. All right. Now, in our next example, we're going to look at a real-world application of systems of inequality. So let's look at example 4. A bakery sells muffins for $5 and cookies for $2.50. The goal each day is to sell at least 50 muffins and cookies and make at least $200 in revenue. So we're going to write a system of linear inequalities to model the constraints in the problem. So we know if we let x equal the number of muffins and we let y equal the number of cookies, then we know that the number of muffins plus the number of cookies, they want that to be at least, so greater than or equal to 50 items. All right. Now we're going to write an inequality for the value. So the muffins were $5 each, so 5x. The cookies were $2.50 each, so 2.5y. And they want to make at least, so greater than or equal to, 200 in revenue. Now we have a couple more constraints here because the number of muffins must be positive. So that would be x is greater than or equal to 0. And the number of cookies, so y must be greater than or equal to 0. All right. Part B, graph the system by finding the intercepts of each constraint. Now here's what that means. We have x plus y is greater than or equal to 50. So I'm going to use the cover-up method here. The cover-up method means if I cover up the y, what I would have left, and I'm not going to use inequality here, I would just have x is equal to 50. If I covered up the x, I would have y equals 50. So that means I have an x-intercept of 50, 0 and a y-intercept of 50, 0. So let's plot those two. Let's see. 50, 0 on the x-axis, 0, 50 on the y-axis, and that should be a solid line. Now, the symbol is greater than or equal to, so we're going to shade above. So I'm going to draw an arrow indicating to shade above. Now, for the second inequality, 5x plus 2.5y greater than or equal to 200. To find the x-intercept, you take the x term, which is 5x, and make it equal to the constant term. And then when you divide, 200 divided by 5 would give you 40. So that means I have an x-intercept of 40, 0. To find the y-intercept, I take the y term, 2.5y, and make it equal to 200. Now divide both sides by 2.5 here. So 200 divided by 2.5 gives me 80. So 0, 80. So I'll do this line in a different color. I have an x-intercept at 40, 0, and a y-intercept at 0, 80. Connect this in a solid line. And then it is also greater than, so I'm going to be shading above. Now, x is greater than or equal to 0 is this axis, so we'll be shading above. Y is greater than or equal to 0 is this axis, so we'll be shading above. So the commonly shaded area here is this region. So in this problem, we did not form a triangular region. It's a more open-ended region, continuing to infinity. Okay. In part C, it says show that 30 muffins and 40 cookies is a solution. So this is your, whoops, I need a pen here. This is your x and this is your y. So on the x-axis, I want to go over 30 and up 40. And that would land me right in here. I'll label that point, 30, 40. And notice it's in the shaded region. So that proves graphically that it's a solution. To prove it algebraically, we must write down our original inequalities and then plug in our ordered pair. If it's truly a solution, it's going to make each inequality true. So 30 muffins plus 40 cookies, is that greater than or equal to 50? Well, 70. So yes, it makes this inequality true. All right, let's do the same thing over here, but let's replace the x and y with parentheses. And I will plug in 30 muffins and 40 cookies. Now I'm going to need my calculator for this one. 5 times 30 plus 2.5 times 40 gives me 250. And you ask yourself, is 250 greater than or equal to 200? And sure enough, it makes that inequality too. So now we've proved graphically by looking at where the ordered pair fell on the graph, and we've proved it algebraically that it is a solution. So that concludes today's lesson, systems of 3 equations in 2 variables.